Okay, good morning everybody, and welcome to the next session on basics of video technology. So last time we finished with modulation. So we saw QAM, SSE, FM, and now we want to come to digital filters because we saw in the process of our amplitude demodulation we need low-pass filters, right? Analog or digital, we need low-pass filters. And we already used the L filter function last time for the AM demodulation in the digital interval. So the question is, how does it work? Right? What's behind this L filter function? How does digital filtering work? Right? So let's start with first taking a look at the help function of L filter in Python. So here we can see it. So we have this L filter function, and we can just import SciPy signal completely into interactive Python. So I'm starting Python. Let's just take Python 3, a little bigger, and now import SciPy, and now we can just type help L filter. So that gives us the description of it. So actually this help function is usually quite useful and helpful because it tells us first what's the arguments, what's the input, what's the output, what's the meaning of the arguments. And it also gives us usually some background about the function itself, what it does. So here we can see the parameters. We have B and A. So B is a numerator coefficient array, which came out of Ramus, for instance. And A is the so-called denominator coefficient array, which we will see what it is. So let me go on. X is actually the sigma that we want to filter. So this is the array containing the samples of our signal that we want to filter. And axis is only needed if we have a multi-dimensional signal so that we can tell the function in which direction it should do the filtering, horizontally or vertically. So this is, for instance, relevant if we want to apply it to an image. Then we can tell it along which direction it should filter. And Zi is an optional array containing internal memory elements, which we also will see what it does. So then it returns an array Y, which contains the filtered samples, the low-pass filter, for instance. And ZF is now the new internal memory states after filtering. So this is useful, for instance, when we want to do filtering in blocks, right? To make sure that the memory state from the old block is also the beginning memory state for the next block. And then here's some references to related functions. And here is the description of the function itself. So here you can see in this first equation here what it actually does. So here you can also see the meaning of those coefficients. You can see Y is the output of this function, X is the input, and here you can now see the coefficients in action. Right? You can see the output, the scaled output, scaled by A0, so that's actually why usually A0 is chosen to be 1, so that it, you can forget about this coefficient here. Is simply a weighted average of past input samples, where the B's are the weights for the input samples, and the B's can be positive and negative. And it also has as input past output samples weighted with the coefficients A. Right? Remember, B were the numerator coefficients, A were the denominator coefficients. Yeah. And you can can see it goes up to n and m, where this is the degree for the numerator and the denominator. So basically, this explains everything about the filter in principle. But maybe it's not so obvious just looking at this formula. And that's why I want to take a closer look at what a filter is actually doing. Right. So this is the key formula here. So it's also here in the script. So basically, I just took this equation from the head function and put it here, and then translated it into a mathematical notation using those sum symbols. It's the same thing, but just using a slightly different notation. So here again you can see the first sum has the B coefficients. It's basically a weighted average of past input samples, and also the current one if m is equal to 0. And then the second sum goes over the past output samples. So this is the weighted sum of the past output samples, which also goes into the current output. But now this sum starts in 1, right? So that we don't have the current output sample, because the current output sample is what we want to calculate with this sum, so we cannot have it as an input here. Right? Otherwise we're in trouble. So here this sum starts at 0, so that we also have the current input sample, which is available. Right? But the second sum starts at m equals 1, which is the output sample 1 in the past and then earlier ones, which we also have available in our memory. Right? So when we look at this equation, we see that this is actually a convolution. Right? You have two convolution sums. So here we have convolution sums of past input values, including the latest, the current value x of m, and past output values y, excluding the current one, right? To avoid a loop without delay. So two convolutions, and convolution is something that we already saw when we went from the FFT or the DCT domain back into the space or time domain, when we applied our mask. Right? The mask was element-wise multiplication in the frequency domain. And element-wise multiplication in the frequency domain is convolution in the time or space domain. So here you can see that indeed now we have this convolution that we saw from our filtering process. So, makes sense. Yeah, does everybody recognize it? So we have two convolution sums. Basically what's new here is the A's. So far we didn't really look into a feedback loop of a filter. What we did so far is the first sum convolving a coefficient sequence with the input. Yeah, and such a filter has a name. It's called Linear Time Invariant System, or short LTI system. Right. And it's because it complies with the linearity and time invariance rules. So these rules are like follows. We have some linear time invariant function f. So f should be now some abstract function, a function of a sequence. So this f might be our L filter function. Right. So x is our input sequence, and then we say that f is linear when we have two signals, x1 and x2. For instance, two different audio signals. And we add them. Then if we apply this function to the sum of the two signals, it's the same as if we first apply the function to each signal individually and then summing at the output. Right? So if f is linear, then it doesn't matter if we do the summation before or after applying this function. Right? This n here,
Yeah.
well, it's anything you want. It depends on the signal, right? So I didn't specify it because it's a very general formulation for linearity. So this n usually is as long as the signal. So if you have a video signal, then it's as long as your video signal, or if you have an audio signal, then it's going along your audio signal. So basically it has no limit. Yeah. And for instance, in our AM example, if we have x1 is our signal and x2 is noise, then we can write it as applying this function, this low-pass filtering, first to the pure signal and then separately to the noise, and then add the low-pass noise to the low-pass signal. Right. So that's convenient for reformulations, because here we can basically extract sums and hence also factors from the function. Right. So from this basically we can also deduct that we can take a factor out of this function. So if you apply this function, this L filter, to a signal which has an amplification factor, for instance, then it doesn't matter if we apply this function, this L filter, to this amplified signal, or first apply this function to the signal and then amplify with the same factor. You can basically extract this factor here. So it doesn't matter if you apply this factor before or after filtering. Make sense? So that's very convenient because it allows you to reformulate the function. Time invariance basically means it doesn't matter when you apply a function, it stays the same. So if you have a function, you apply this function to some signal x, you get a low-pass output, for instance, or you take a shifted version of the same signal. Right? Now you have the same signal, but just delay it by n naught samples. Right? Basically, the signal comes later. Then that's the same as taking the previous output and shift it. Right? So the only difference between the two versions is the shift. So a shifted input leads to accordingly shifted output. The function doesn't change with time. It's time invariant. Yeah, makes sense? So this is for some generic shift and not. Yeah, so our desired low-pass filter should now work like our mask in the Dft frequency bands, or filter for our image for the subsampling, like in slide set 4. It should get the signal components at high frequency as close as possible to 0, which means it should attenuate, but at the same time leave the signal components at the desired low frequencies intact. Unchanged. Yeah, our mask or filter in the Dft frequency bands, or the transfer function, or desired transfer function, should therefore ideally have a factor of 1 at the desired frequencies that we want to keep, and a factor of 0s at the unwanted frequencies that we want to get rid of. So let's call our frequency index in the Dft domain k, which as before, and then our transfer function of our filter depending on the frequency index as h of k. So k is now the argument of this transfer function. Right? So this is basically for each frequency bin in the Dft, we get a factor h. So for low k, this h should be, for instance, 1, and at high case it should be 0. And if you have a filter design, then you will get factors h, which in general can be complex valued, because a Dft is a complex valued transform. Make sense? So, to calculate whether our filter does what it's supposed to do, we have to calculate the DFT of the entire output signal y of n. Right? So this is our low-pass filtered signal, and then we can apply the DFT to see if it still contains high frequencies or not, or if it does, how much. Right? So we apply it to the signal or a part of it. And for this, we treat the signals x and y again as vectors of the desired length, given the length of the DFT. So for instance, we can say we take a DFT of length 1024, and then we apply it to chunks or blocks of 1024 of our signal. So the linearity of the DFT helps us here. So the DFT, we know, is a linear time invariant system with the properties that we just saw. So we can simply use those properties. First, the linearity rule, which you can see here. So here we know the DFT, if it's linear, the DFT of the sum of two signals is the sum of the DFT of the two signals. And the DFT of an amplified signal is the amplification of the DFT of the signal. Yeah, in our convolution sum, also the delayed versions appear, right? The convolution sum has the terms x of n minus n and y of n minus n. Right. So when we look back at our convolution sum that we saw here, right? So here you can see x of n minus m, and here's n y of n minus m, where m was the sum index. Right. So we have shifted versions, shifted by m samples. Yeah. Except that above I had rectangular brackets because that came from the Python L function, and here I'm using round brackets because that's my usual notation. Right. So it basically doesn't matter, I use it in the same meaning here. So what is the DFT of those delayed versions of our signal? So for that purpose, we can look again at the definition of the DFT from slide set 4. So here we can see the definition of the DFT. It's the sum over n samples, and n can be chosen by us, for instance 1024 samples. And we can simplify this calculation by first use this abbreviation. So instead of e to the j 2 pi times k divided by n, we just write z. And then z will be just a complex number on the unit circle. Right? Remember, this exponential e to the j something is always on the unit circle in the complex plane, and the 2 pi k divided by n is the angle of this pointer towards the unit circle. Make sense? So the exponent here gives the angle, and it always has length 1. So this is our z. Basically, now z is the number in the complex plane on the unit circle. Yeah, and we can do that conveniently because this factor is not depending on index n, right? So I conveniently left out this lowercase n here in the sum. And then
how about the negative?
Yeah, what about the negative? I ignored it, right? So for now, z is just this factor without the minus. So that means we have to remember this negative sign, right? Basically, we have to remember this negative sign at the end, right? They are still there. They are not absorbed by the z. Right? So this is what we have to keep in mind. We absorbed everything except for the sign and the n. So when you look at the z here, it contains exactly capital N uniformly distributed points on the unit circle, right? Because k goes from 0 to n minus 1. So basically we sample the unit circle in this way on the complex plane. And this z now also contains the frequency index k. So we already absorbed k into z. Right? Z is now containing the k internally. So if we want to change the frequency, we have to change z. Right? It's basically, this k changes the angle on the unit circle. Yeah, and since this factor z now also contains the frequency index k, it also appears as the new argument on the left-hand side of our DFT equation, and we get this simplified version. Right? So instead of x of k, we now have x of z, because that contains the k. And instead of this e to the j something, we now have z to the minus n. So here you can see the minus sign, the negative sign, and the n. Right? That's basically everything that we left out from z. Make sense? So this is basically now still the same as the DFT if we choose z accordingly. Right. So now we have a general expression. So looking at this general expression, we could get the idea to use not only the n complex points on the unit circle of the complex plane for z, but also arbitrary complex numbers, right? Which simplifies the mathematical analysis and processing. Right? So why limit ourselves to those n points on the unit circle? This equation works for any complex number z, right? At least mathematically. And because it's convenient, this is actually done. So this is indeed done. And in the above expression, for a sigma sequence of length n, this transform is called z transform. Right? Kind of obvious because we now have a z instead of this complex exponential. Have you heard about z transforms before?
The term, what it is.
Hmm?
We've heard the term that it exists, but not really.
Okay. Yeah, so you should memorize this equation because this is basically always used when we have time discrete or digital signals. So this is the z transform. Z transform for causal signals starting at n equals 0, and this is basically always used when we have time discrete signals, which is most of the time. Because this is more generic than the DFT. At least mathematically it's very convenient. When you want to analyze numerically a system, then usually a DFT or the FFT is used. Right? But for the theory, usually the Z transform is used. Yeah, so in this transformation, we can simply use x of n minus n to obtain the Z transform of our delayed signals. Right? Remember, we want to know what's the result of the DFT or the Z transform, in this case, for this delayed signal which comes out of our convolution equation, since we want to analyze the convolution. So we have a delayed signal, and this delayed signal has a Z transform, which I call x delayed of Z. So now we want to know how this x delayed Z relates to x of Z. So note that the sum index here is m, and n is assumed to be a constant delay in the following. So we can just adjust the range of the sum to the shifted range of the signal. Is that true? The sum index is m? Yes. And n is assumed to be a constant delay. So here's the z-transform of our delayed signal. So you can see here the sum, then you have the shifted or delayed signal x of m minus n, where m is our sum index, and then z to the minus n for each of those samples. Make sense? So I just adjusted the boundaries of the summation because of the delay of the signal. When we assume that the signal starts at sample number 0, then the delayed signal starts at sample number n. Right? That's why we start the sum here at sample number n. And since we delayed it, it also ends later. So here it goes up to n minus 1 plus n. Right? It's the same range, but shifted. So now to see the result of the z-transform, we make this index substitution. We replace lowercase m by m plus n. So we shift it basically. So then we have the original range back for our sum. So this new m now goes from 0 to capital N minus 1. Also, the argument of x is the same. But now we have minus m minus n in the exponent. So now, instead of having a shifted argument of the signal, we have a shifted argument in the exponent. This is what we achieved with this index substitution. Yeah, and this is convenient because we can simply factor out the z to the minus n. Right? We know that z to the minus n is z to the minus n times z to the minus n. Right? And since z to the minus n is not affected by the sum index, we can just factor it out of the sum, and we have it here in front of the sum. We have just z to the minus n here. And then we can see the sum itself is the z-transform of the original signal x without the shift, without the delay. Right? So altogether we have z to the minus n times x of z, where x is the non-shifted version. Yeah. So here we see the z-transform, let's call it z-transform, shorter of the signal, shifted or delayed by n values is a z-transform of the undelayed signal. Multiplied by a factor z to the minus n. And this is also called the delay rule. So here z-transform on the undelayed signal multiplied by this factor. Yeah, does it make sense? So using this index substitution, we were able to factor out the z to the minus n. And this is very convenient because now we can turn a delay into a factor in the z domain. Right? Remember, we have those shifts, delays in our convolution, and it's really difficult to reformulate delays of a signal. It's basically impossible, except for this index substitution, which is kind of tricky. Right? So now we achieved to basically reformulate the delay in the z-transform as a factor. And when we have sums of delayed signals in the time domain, then we have factors of the original signal in the frequency domain, and then we can just simply factor out those factors from the sum. Right? So this is what we will do next. So now we have all the necessary tools for the closed form calculation of the Z-transform and thus the DFT of our filters above, the L filter. So now we can analyze what this L filter is doing. It allows us to calculate the transfer function of this filter. We can find a closed form general solution for this L filter function for some arbitrary b's and a's. So again, we start with a description coming out of L filter, this function, this formula here, right? And then we simply apply the Z-transform to it. So the Z-transform of the output is now obtained by using the linearity rule and the delay rule. And you can see the result down here. So here you can see on the left hand side we still have this constant A0, right? It stays the same. But instead of y of n, we have its Z-transform y of z. Right? So we just replace lowercase y of n by capital Y of z. So this is how we denote Z-transforms. Then on the right hand side we have those sums, and we can see the first sum contains x of n minus m, and x of n minus m is simply x of z times z to the minus m. Right? So we replace each of those expressions here by z to the minus m times capital X of z. Make sense? So since x of z is the same for all the summands, we can factor it out. And we get this factor here in front of the sum. And what's left inside the sum is simply the factor from the delays. See, this is what I mean with simplifying the sum for different delays. Right? This allows us to factor out the signal. So now instead of having different versions of the signal, we just have one version, capital X of z, followed by a sum as a factor. And this sum contains the z to the minus m, which now are from the delays. Right? So instead of having the signal in the sum, now we simply have those coefficients b times z to the minus m. And you can see that this sum here is totally independent of the signal. It's only a property of our filter, of the filter coefficients. Right? There's no x in the sum anymore. Same for the second sum. We can factor out the y, capital Y of z, as a Z-transform, and then what's left from the sum is simply the fixed coefficients a times the delays, z to the minus m. Make sense? So it's very convenient for obtaining a closed form solution for this analysis. Right. So this is now our output in the z domain, and now we can compute the transfer function. So the transfer function basically tells us how input and output are related. Right. This pass band has factor 1, the stop band should have factor 0. So basically our transfer function is the output divided by the input. And in the Z domain or the DFT domain, we just take the output at each frequency bin and divide it by the input at each frequency bin. And the same here in the Z domain. Right. So we have the output for each possible Z divided by the input for each possible Z, where the Z is then on the unit circle. So to get a closed form solution for our transfer function, we simply bring the y's on one side and the x's on the other side. So we can see here we had this y times a0 on the left hand side and then y times the sum on the right hand side. now we just bring this sum on the left-hand side, and that also turns our negative sign now into this positive sign, which is nice. So here you can take a look. So here we had this expression minus y times the sum. We just bring it over to the left-hand side, factor out y, and then we get this expression. So a0 is left, plus the sum from the right-hand side, which contains the coefficients a and the z to the minus n from the shift. And this is what's left from the right-hand side. Make sense? So simply bring the x's and the y's on one side. So now we can divide both sides by the factors of y and x, and thus obtain our desired transfer function. So here now we have y divided by x, so we bring x on the other side by division, and then the sum of y on the right hand side by division, and this is what we get. So here this sum goes from here to here, and the x goes from here to here. Make sense? So now we have a closed form solution for our transfer function. So this is now a fraction whose denominator and numerator are polynomials in Z. And interestingly, this not only works for Z on the unit circle, but basically for any arbitrary Z. So that's still an interesting generalization, right? To see Z not just as the unit circle, but more general complex numbers. Yeah, so in general we have now two polynomials, right? And now you can also see why B is called the numerator coefficients and A is called the denominator coefficients. Right? Remember, we saw those expressions in the help function of L filter, A being the denominator and B being the numerator. And now we know why they are called this way. Right? Because in the Z domain, the transfer function really consists of two polynomials, one in the numerator and one in the denominator, and the coefficients are accordingly in the numerator and the denominator. Right? So the B's are really in the numerator and the A's are really in the denominator. And that's why they have this name. That's where they appear in the Z transform. Yeah, and when you look at these expressions, they themselves look like Z transforms. Right? So when you look at the numerator polynomial here, you can see it is the sum of B of m times Z to the minus n. It is basically the same as the sum of x of n times z to the minus n. Right? So basically what we see here in the numerator is the Z transform of the sequence B. Same here in the denominator. And here you can now also see why we need this A0, because the sum here starts at 1. Right? And if you include this A0, then we have the Z transform of the A coefficients. So the transfer function is simply the Z transform of the B coefficients divided by the Z transform of the A coefficients. Yeah, so Z transform coefficient vectors. So now we have B of Z and A of Z as the Z transforms, and this is this simplifies the transfer function again. So now we can simply write H of Z equals B of Z divided by A of Z. So it's all Z transforms. Simple, right? at least at this point, it becomes very simple because you just have a fraction, a very simple fraction of two Z transforms. Yeah, and this can be used for theoretically analyze this transfer function. For instance, by looking at the poles and zeros of this transfer function. Right? The zeros of B gives us the zeros of H, and the zeros of A give us the poles of H, basically where H becomes infinity. Right? And those poles, they don't have to live on the unit circle, they can be anywhere in this complex plane, and the location gives us a lot of insight about the properties of this transfer function. So that's another reason why the Z transform is so useful, because we can analyze theoretically the properties by looking at the zeros of those two polynomials and their location. Remember, each polynomial of nth order has how many zeros? Yeah.
N.
Yes, right. So the more coefficients we have, the more zeros and poles we will have. And their location can be computed. Usually you would use, for instance, Python for it. Python has a function which is called roots, and this function roots computes the locations of the zeros of a polynomial. Yeah, so if you want to calculate and plot our frequency response, we simply need to evaluate this transfer function on the unit circle. So basically we just need to replace z by e to the j 2 pi k divided by n. Right? So basically replacing it back. That means we get this formula here, and now we get a function with argument k, and k is then the frequency bins again, from 0 to capital N minus 1. And for each frequency bin, it gives us a complex number with magnitude and phase, basically, and then we can plot with magnitude, we can see where the passband is, and the phase, we can see the group delays for different frequency components. Yeah, so then basically we are arriving at this fraction here in the DFT domain. Right. So given k, we have the values of bk and ak, and this fraction then results in the transfer function. And this is basically exactly what the function frexy in Python's SciPy signal library does. Right? With frexy we can analyze our design. Remember, we already did that in our AM design. We used frexy to plot the resulting magnitude response. And what frexy does is exactly this. It takes the transfer function and evaluates it at n different frequency points for k equals 0 to capital N minus 1. And this has a default standard value of length n equals 1024 for 1024 frequency points between 0 and 2 pi. 2 pi is our sampling frequency. It actually starts exactly at 0 and ends just below 2 pi, right? Because 2 pi is identical to 0. Yeah, and since the vectors of for coefficients a and b are usually much shorter than this 1024, right? What frexy is doing is basically it fills those sequences up with zeros, so that we get DFTs of length 1024. So they are zero padded up to length of 1024. So for instance, the first few coefficients, I don't know, maybe 4 coefficients in the beginning are non-zero, and then the rest is all zeros to fill it up to 1024. Right? And then you have your A of k and B of k. And by default, only the lower half of this range is displayed by this function, meaning only 512 frequency bins up to Nyquist. Because when we have real valued coefficients, then we have the symmetry. And then the second half doesn't give us any extra information. Yeah, does it make sense so far? So now we have a possibility to analyze our filters. So here a Python example. So for our AM demodulator, we needed a low pass with the upper cutoff frequency of 500 Hz at 1600 Hz Nyquist frequency, which means 32 kHz sampling. Right? So we calculate our filter coefficients with the function IIR filter, and we want to check the resulting coefficients, right? Because we never know what you actually get. You can, in the argument, you can give your wishes, but it's not clear if your wishes will be fulfilled depending on what combinations of arguments you have. So we start with Python. So not IPython in the command line mode. And first again import SciPy signal, everything from SciPy signal into our namespace. Then also SciPy itself, then matplotlib, pyplot as PLT for plotting. And in the next line we do the filter computation, IIR filter. And you see here the first argument is the number of coefficients. So I'm just choosing 2 coefficients for numerator and denominator. Right, so we have A of length 2 and B of length 2. Then here we have our cutoff frequency, 500 divided by 1600, because this is the normalization that IIR filter expects. It normalizes to the Nyquist frequency, so that Nyquist is 1. And here is the desired attenuation in dB, 60 dB stop at attenuation. This is my wish. I'm not sure if I'm getting it, but that's my wish. And here filter type is low pass. Because you can also do high pass, band pass, Remis, maybe Remis, I'm not sure. I mean Hilbert. Yeah, so this is actually what you can see when you look at help, what arguments you can use. Let's see. No, that was L filter. Let's type help IIR filter. So here you can see the description of IIR filter, and you can see the first argument is the order of the filter, the number of coefficients we get for numerator and denominator. Then the second one is an array giving the critical frequencies. In our case, low pass, we only have one critical frequency, which is the cutoff frequency. Yeah, so it is normalized to 0 to 1, where 1 is the Nyquist frequency. Then RP provides a maximum ripple in the pass band, which we don't have here, but here RS for the stop band. And here you can see we have different types: band pass, low pass, high pass, and band stop. And this is not so interesting because you only need to digital filters. F type. So here we can actually choose different design methods. And you might have seen those types also from analog filters, because, for instance, Butterworth is also an analog filter design method. Have you seen Butterworth design, filter design? Not really? Yeah, so basically these are just different design methods which give different properties to the filter, and you can actually try out what works best for your application. So default is, let's see, optional, the type of our filter to design. It doesn't really say which one it does by default. Interesting. Yeah, and it returns the B and the A arrays for the numerator and the denominator. But here you can see alternative design functions. So it's always worthwhile to check out the head function because it gives us the necessary information very briefly. Right. And also some references here. Okay, so then let's just try it. So here is our function, copy and paste. See, it's already done. And now we can see what's in it. B. So this is B, and here is A. Ah, interesting. So it actually gives you 3 coefficients for B and 2 coefficients for A. The first one is always 1. So it's actually just 2 coefficients for A. But it seems 2 means the order, which means 0, 1, 2. Right. So that's why you have 3 coefficients here. Make sense? So now it's hard to tell if these numbers are good or not. Right? Just by looking at it, it doesn't really say much. And that's why we need the function fraxi. Right? Here, this fraxi. Again, first look at help. Fraxi to see how it's used. So here you can see first argument is B, the numerator coefficients, then it's A, the denominator coefficients, and by default it's 1. So if you don't specify it, it's assumed that only the default coefficient is there, which is the 1. Then here this is the number of frequency points that you could specify here. Whole means if you want to have the output from 0 to pi or from 0 to 2 pi. By default it's 2 pi. And here you can also specify some plotting function if you want. Yeah, so this computes the frequency response of the digital filter in this way. So here again, you can see the transfer function now in the formulation of the in the DFT domain. Right, so here you can see now e to the j omega. So this is our DFT domain, or DTFT domain to be more precise. Right, and you can see the meaning of those arguments. So default is 512 frequencies equally spaced around the unit circle. And whole, normally frequencies are computed from 0 to Nyquist or pi. If whole, then it computes from 0 to 2 pi. So to sampling. And this is relevant if you have complex coefficients, right? Complex filters. Yeah, it returns, first return is W, which is the normalized frequencies at which the frequency response is computed. So this is convenient for plotting. And H is the complex valued frequency response. Right. Makes sense so far? Okay. Yeah, here are some examples actually. So examples are always good. So basically I'm just using the first 2 arguments, B and A, and leave everything at default. So here I'm now pasting it. And now you can see here when I type W, here you basically get the frequency points. And you can see here it goes from 0 to pi. So observe now, this is really pi, not 1. Right? So there's a different normalization between Frexi, which assumes Nyquist is 1. No, IRR filter, which assumes Nyquist is 1, and Frexi, which assumes Nyquist is pi. So this can easily lead to confusion, so keep it in mind that you have those different normalizations. Filter design, you want to have Nyquist equal to 1, but for analysis, Frexi has Nyquist equals pi. Right. So here you can also see that it starts with 0 when you go up. So right in the beginning you have 0 and then you have increasing values. So you have 512 values. Yeah, 512 values here, and increasing from 0 to up to, but excluding pi. Yeah, and then we can plot it, which I do next. So first I take the absolute value. Here I'm just taking psi pi absolute, but abs should also work. So pasting it. Import psi pi. Yes. So now I can plot the magnitude of our transfer function, which is important to see where we have the attenuation over the frequency. So here I'm plotting, say W, comma. So here we actually have the choice. We can plot it with x, with W as the x-axis, which is the normalized frequencies, or we can say we have this frequency index k. So in this case, I'm just using the frequency index k, which goes from 0 to 511 here. But in general, we would plot the normalized frequencies because it's more instructive. So actually, we could try both. So first, this one here. Copy, paste. Ooh, interesting. I need to import matplotlib. Copy. First importing the matplotlib, and then doing the plotting. X label, Y label, title, and show. And here we go. What do you think? It looks like the AM low pass that we used, right? And here indeed, we now have the frequency index k, where 512 is our Nyquist frequency. So these are the frequency bins that our DFT computes. And we can see here's the pass band in the beginning, and here we now have our stop band, where we attenuate. But we saw when we plot this in dB, actually this filter is not, maybe not that great. It's okay, but not that great. Right, so this is what we get. So this is exactly what we got in slide 8b. Except that now we see directly the DFT index k on the x-axis. Right, to see more clearly what the frequency is doing. instead of normalizing to pi for the Nyquist frequency, which you would normally do using plot x comma plot w comma h. Yeah, and then we can also analyze it in the z domain. So more theoretically instead of numerically, we can analyze the behavior of the filter directly in the z domain. Let's call it z domain instead of z range. So we have a fraction of polynomials here. Let's assume we have a polynomial of order 2, which we do. Then we have this, right? We have a numerator polynomial and a denominator polynomial. You can see here in the numerator we indeed have 3 coefficients from 0 to number 2. And in the denominator basically we have 2 coefficients because the first one is always a 1. Which for the analysis, the mathematical analysis here doesn't really matter. And we can actually factor out the z to the minus 2 to make the exponent positive if we want to. So polynomials of order n have exactly n zeros or roots. That means here we get 2 zeros each in numerator and denominator. And the zeros in the denominator are also called poles, or poles of the fraction, because the value of the fraction there goes towards infinity. Right? We have something divided by something very small, then it goes to infinity. The zeros in the numerator are simply called zeros of the fraction. So by knowing the zeros and poles, we are able to convert the polynomials into a product of first order polynomials. Right. So assume we have those 2 zeros for the numerator, z0 and z1, and the 2 poles, p0 and p1. And some constant c. So the constant doesn't really matter because we can always correct for some constant by a fixed constant. So we see we get products and ratios with simple differences. So we have z minus something. Right? Are you familiar with this formulation? Writing a polynomial as a product of their zeros. So here we have z minus z0, z minus z1, and the same here for the denominator. So we can always do this reformulation. It comes out of polynomial theory. Yeah, suppose we want to calculate or estimate the magnitude of the transfer function, magnitude of h of z, right, which we just did in our plot of our frequency response. We just took the magnitude of h. So this is what I'm doing here now, mathematically. So magnitude of h is magnitude of c times all the magnitudes here. Right? So we just have a product and division of magnitudes. And the magnitude here is basically just the distance between the current z and then the zeros, z0 and z1, or here the poles, p0 and p1. Right? So each of those magnitudes are distances. So when you say one complex number minus another complex number, these are points in the complex plane, and you can actually measure the distance in this complex plane between those complex numbers. And this distance is the magnitude. Make sense? So just measure the distance, gives you the magnitude. Yeah, so for our estimation, we simply replace z by our unit circle, by our points on the unit circle, so that z will go over the unit circle in the complex plane. So basically, we drive along the unit circle. starting at angle 0 and then going up. And then for each point on the unit circle, we can compute the distances to the zeros and poles. Right? And basically then we measure each distance on the numerator part, multiply them, all those distances, and we do the same for the poles. We take all the distances to all the poles, multiply them, and that's our denominator. And then we have the division. And that means when we are close to a pole, we get a very small number. Right? A product with a very small number is again a very small number. And if we divide by a very small number, then we get a large output. Vice versa for the numerator, if we have a very small number in it, if our z is very close to a 0, then the output will also be very small. Right? So that shows us if our z is close to a 0, the output will be very small. If our 0 is close to a pole, the output will be very large. Right? And this is how we can actually estimate what type of filter we have. Yeah, so the most significant changes in the frequency response magnitude occur at the closest proximity of z to one of the poles or the 0 points. Right? In the vicinity of a 0 point, it will quickly decrease. In the vicinity of a pole point, it will quickly increase in magnitude. In this way, the magnitude of the frequency response can be visually estimated by the position of the poles and zeros in the complex plane. And this is what I mentioned earlier, right? Basically, just by knowing the location of the poles and zeros allows us to see what type of filter we have. So here's a Python example. So we can take our example of the low-pass filter again and now calculate the poles and zeros using roots, right? Our function roots in NumPy. We should turn on the light. So this is very convenient because it calculates those zeros for us. And we just need to give the coefficient vector as argument. So here we do it. So I already imported those libraries. Here's our filter, which we already did. And now we have Nullstellen, which is zeros, using our coefficient vector b. Right. So here, copy, paste, import NumPy, import NumPy as MP. So again, yes. So let's see, Nullstellen. Yeah, so in our case, we have two identical zeros, both located at -1. Right? -1 is what angle in the z-plane? Yeah, which means which normalized frequency? Remember, we have this e to the j omega, that's normalized frequency in the complex plane, this pointer. So omega is 180 degrees or pi, right? And pi is what frequency? Nyquist, right? So this angle in the complex plane is identical to our normalized frequency. And this comes from our substitution, right? We had this e to the j 2 pi divided by n times k. This 2 pi divided by capital N times k is our angle, which is at the same time our normalized frequency. Right? So basically, making this substitution, z equals e to the j omega, means that in the complex plane, this angle is identical to our normalized frequency, where pi is Nyquist. Make sense? So So this is actually, this is S of j times pi means normalized frequency pi or Nyquist. Does it make sense? Or should I explain it a little bit more?
Can you explain?
Okay. So this basically comes from, here from this replacement. Right. So here we can see, for instance, or Nyquist frequency here is k equals n divided by 2, or, makes sense? So n goes up to sampling, so kn equals n over 2 is Nyquist, and then this would be z equals copy. So if k equals n over 2, what is this then? It's just pi, right? So k is n over 2, that means we have 2 down here, the 2 cancels, and all that's left is the pi. You can also make it a real pi. Right? And this is minus 1. Right? Yeah. This means if we see z equals minus 1, this means the Nyquist frequency. Does it help? Okay. Yeah, so basically this is the result of this substitution. Z equals e to the j 2 pi k over n. This means in this way we have this equivalence between normalized frequency and angle. Yeah. And making the equivalence between z and the complex exponential means we get this equivalence between the angle of z and the normalized frequency. So here angle and normalized frequency. Yeah. So this is the important point. it tells us the normalized frequency. So here we can now see it. These are two complex numbers, right? Each giving us the location of a zero, and each being at Nyquist. Right. So going back to my example. Where is it? Yeah. 2, 0 locations. Each at, so that means we have a double zero. We have a double zero at Nyquist frequency. Yeah, so this actually means that we probably have a low-pass filter, because the low-pass filter should have no output or as little output as possible at the highest frequency. So basically here we have a double zero. Yeah, this means we have no output at the highest frequency Nyquist. So it's probably a low pass filter. Or could also be band pass filter. It depends now on the poles. So now we can take a look at the poles here by applying the roots function to the array A. So here we have pole. And here we can see we get two locations which are not so simple. Right? So you can also see that they are conjugate complex, because the real part is identical and the imaginary part is just sign changed. So we have a conjugate complex pair here. Can you see it? So this now has an angle which is a little bit more complicated. It's not so obvious. You cannot really see it immediately. So here you can see again the numbers. So now we can plot the pole and zeros in the complex plane. The poles as an X and the zeros as an O. So I'm just using the plot function, using the real part as X and the imaginary part as Y-axis, and put an X at the position. And I do the same for the zeros, just placing an O at those positions. Right. So I do that here. Copy, paste. So what comes next? Yeah, we can make a suitable axis scaling, and we can also plot the unit circle, so that we can see where the unit circle is. And where it is. Give it a title and show it. This looks a little bit skewed because the window is skewed. Let's make it a little bit more nice. So now you can see here is the complex plane, X is real part, Y is imaginary part. Then you can see the unit circle in green, and you can see those two blue crosses, which are the locations of the pole. And you can see the two poles are indeed conjugate complex and inside the unit circle, which means this filter is stable. Right? It's not exploding. It's not getting bigger and bigger, but if you have an input and then you stop the input, it decays and goes back to 0. And here you can see the two zeros at Nyquist at -1. So when you now go along the unit circle starting at angle 0, then first you come close to the poles. That means the output gets really large. Right? This is the pass band. And then when you continue to go with larger angles, then you come close to the 0 at Nyquist. That means the output is getting smaller and smaller until you have no output at pi, at angle pi. So you can imagine you basically obtain the transfer function by going along the unit circle, starting here at 0. Here you get the largest output in this vicinity. Then you go on and on and on, and here you get the lowest output, which is 0 at this point. And this is then Nyquist. So at that point you would stop because we only have real values here, real values. Make sense? Okay. So in this way we can actually see the resulting filter without computing it. So here you can see the result again. So here 2 zeros at -1. So we move counterclockwise on the unit circle, starting from z equals 1 or 0 degrees, and then go up to pi or 180 degrees. Yeah, and we can see that poles are within the unit circle, which means the filter is stable. Yeah, and here I also have a little Python example. So maybe I can quickly do it. Open it here. Copy. Quit. So gedit. So here you can see this program, and you can see here is setting up the libraries. Here are the constants for the sound card, and here is the filter, the IR filter. This is exactly the filter that we just designed. Right? This IR filter, 2 coefficients, cutoff frequency 500 Hz, sampling frequency 32,000 Hz, 60 dB stop attenuation as a wish, and a low pass. And you can see we plot the resulting frequency response again. Here we open the sound card, and here we have the loop over the samples. Here we read the samples from the sound card, converts them to floats. Then we apply this low pass filter here to the floats samples. And we do it block by block, and that's why we need to read in the old memory and write out the new memory. Right? Remember, we have those delays in the filter x to the x of m minus n, and these delays are implemented using memory elements. Right? And these memory elements are the z's. So here, this is the output from the past block, and this is then read in at the next block. Make sense? So this is important to avoid artifacts. Basically returning the old memory content and reading it in at the beginning of the next block. So it always goes from output to the input, so that we have continuous values on those memory elements. Otherwise we couldn't access past values at the beginning of the new block, right? Because it goes into the past block. So we need to know the memory. Yeah, here I do clipping to avoid overload, and then I write it back to the sound card. And let's see what happens if I let it run. Probably I will get feedback. 3. Oh. Test. Can you hear something? Maybe I can quickly attach my speaker.
Bluetooth mode.
Okay. So let's try again. Test. Okay. 1 minute to go up. So this is the frequency response, and this is the filter. So you could hear it's very low passing, right? No high frequencies left. And my voice was actually hard to understand, right? Because it was only consisting of the very lowest frequencies. So this shows you how the filter sounds like, right? So it's really a filter which is concentrating very much on the very lowest frequencies, and everything else is gone. And this is how it sounds. So the speech sounds very dark, almost incomprehensible, because the higher frequencies are all missing, and they are important for speech understanding. Yeah, questions at this point? All clear? Yeah, okay, I guess time is up. So thanks for your attention and have a nice afternoon.